Welcome to the 22nd class meeting of EECE341, the Introduction to Communication Systems. We have several important announcements. First, it's about quiz 2, which will be held on next class meeting. And the TA and I have discussed about the scope and the detailed problems. So what we are going to do is this one. Since many of you were not good at the midterm exam, we are going to recycle some of midterm exam problems, but not in the same form. We are going to little bit modify the problem. So I strongly recommend all of you review the midterm exams. You may get help from the tutor, okay? And also, we are going to recycle the homework problems after the midterm exam. So the homeworks which were not in the midterm scope will appear. And this is the midterm score, which I've shown you in the last class meeting. And especially for this student, I warned you, okay? So if you are here and also around here, be careful. According to my experience, it's very hard for these students to move toward the right direction. And also to around these two students, I'm kind of pleasantly shocked. These two students performed extremely well, and not only in terms of the G score, but also in writing down the solutions in a very neat way and in a very how to say that, clever way. So I'm impressed. And also these two students were very, very good. And I strongly encourage you to continue to do that. So since you have the midterm exam results, you may have now strong interest in voluntary project. So the project, let me tell you, around 80% who submitted voluntary project kind of get promoted in the final grade. So I strongly recommend you to do that if you are, for example, around here, or you are here, but ensure that you get A+, then you'd better do the voluntary project. Here goes the companion courses, which are related to communications and networks. So if you haven't taken Mathematics for EE Engineers A, I strongly recommend it, because as you will see from today, the undergraduate level foundations for communications networking is one, signals and systems. The other is this one, probability and random processes. Without having taken the probability and random processes course, this one, it's impossible to take digital communication. And of course, we need some knowledge on random process in digital signal processing. I haven't yet completely, as I told you, I'm going to teach this course, and I haven't yet completely determined the scope of this introductory digital communications. When I was an undergraduate student, my professor didn't mention much about the random vectors and random signals in the introductory digital communications course, and I agree with him. So I may still remove this one from introduction to DSP. However, if you are planning to take the introduction to digital communications, refresh your memory on this topic that during the winter break, so that you are better prepared. Of course, there will be a graduate level probability in random processes next semester. So, for example, you have already taken this undergraduate probability in random processes, but have interest in reviewing that and also taking credits from kind of duplicating, but not exact, but I recommend this one. I offer this course in spring 25 as an online course. So you can freely control your progress on this topic. And these two courses are very similar and also very complementary. So it will be very, very helpful. Here goes the messages from instructor, myself. So after taking this course, whenever you meet me, I may grasp your neck and say that, what's the messages from me? And your answer must be simplification and visualization. And if you say existence and uniqueness, why not, what if, and scarce resource, abundant resource, blah, 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 then I'll be very, very happy. Got it? So after 20 years, not 20 years, after 10 years, you will have started a 10-bagger startup, and you have too much money to spend, so you come to the university and have a ceremony to donate a lot of fund for your junior students. Then while you strolling around the campus, you suddenly meet me and I will say, hey, what's up? And you say that I have a ceremony to donate a lot of fund to the university, blah, blah, blah. And suddenly I say that thank you. And then what are the messages from me? And if you don't answer one of these, I may kick your knee, okay? So be careful. In the last class meeting, I have some corrections. So I talked about the pre-emphasis filter and de-emphasis filters for the FM receiver and transmitter, where I talked very vaguely and stated something wrong. So let me tell you. So in the according to the history, so this is the this is microphone. This is what happened. So you speak, then microphone converts your acoustic wave to electrical current, and then they place pre-emphasis filter. So this pre-emphasis filter is directly applied to your message signal, and then it is FM modulated. And of course, you have a power amp and antenna. Got it? And in the receiver, you have receive antenna and usually amplifier, which is, what's wrong? Why this set is different from what I usually use? Is this the color what I'm using? Let me anyway use. So there goes LNA and FM D mode. So supposedly here comes the recovered pre-emphasized message filter. So you have here de-emphasis filter. And then, so let me be careful. So here is a speaker. Got it? So pre-emphasis filter basically is a high-pass filter, but although it is not, does not remove low pass. So in frequency domain, it has something like this. Got it? So this de-emphasis filter kind of reciprocates this amplification of high frequency part. Why do we do that? And so this is what happened. And the reason is that we assume our received signal has what? Interference. And this interference is not exactly aligned with our desired signal. So suppose this is our carrier frequency. So we have some FM signal occupying some band. Now, this interference is, for example, is here. Ready? And in order to make everything simple, what we have done is that we assume the desired signal is the FM modulated signal with message, what? No message, actually. So M of t equals 0 means, as you remember, we still transmit a tone, right? Single tone. So here we have a single tone. And if this is received, then what happens? The FM demodulator output will be 0 if we have DC block circuit. However, due to this interference, which is also, for simplification, modeled as a tone signal with some frequency offset from the carrier frequency, that appears as a very loud tone signal. So what we do is that so of course, this one appears here as a high frequency noise. So what we do is that here we emphasize our desired signal's high frequency component. And here we de-emphasize, which means that we attenuate this part so that this amplified one goes back to the normal strength, but this interference appearing here can be just reduced because the interference signal is not pre-emphasized. That's the idea. And during the recorded class meeting of last one, I didn't fully refresh my idea. So I talked about the pre-emphasize and de-emphasize during the FM demodulation. And actually, theoretically, that is still possible. However, this is much simpler because this pre-emphasis filter works on the real baseband message signal. And the emphasis filter is also working on the real baseband signal, that's recovered kind of message signal. However, what I explained during the class meeting, the pre-emphasis and the emphasis filter has to work in the passband. And also, it must be carefully tuned. Otherwise, we have some nonlinear distortion. However, here, since the pre-emphasis filter and the emphasis filter directly works on the baseband, for example, voice signal, even though there is some distortion, as far as interference is a lot suppressed, that is very tolerable. So here goes the correction. So locations of the pre-emphasis and the emphasis filter is what? Pre-emphasis filter follows the microphone output, and the emphasis filter just precedes the speaker. Got it? And second one, in the stereophonic FM, I explained one of the reasons we do not separate right side signal and left side signal as if we place the right side signal and left side signal in the different frequency, and if the channel is frequency selective, then we have imbalanced right side signal and left side signal. Of course, that is also true. However, as you've seen and you will see in the homework problem, our textbook explains also the other reason. It is all about backward compatibility. So this terminology is very popular, especially in modern digital cellular communication. For example, our cell phone supports probably most of yours, not only 5G new radio standard, but also 4G long-term evolution, LTE standards. And when we settle the new standard for cellular communication, it's very important so that the new standard or new chip supports the previous one, something like that. So we do not need to trash the previous standard or trash the previous protocol. That is related to the backward compatibility. And according to the textbook, they say that suppose we have just monophonic FM receiver. And monophonic FM receiver, these two just drive the speaker that makes the sound the sum of the right side and left side one. For example, suppose you recorded two persons' conversation, and this person's voice is recorded on the left speaker track, and this speaker's voice is on the right speaker's track. Now, suppose you just send right side and left side differently, and your old monophonic FM just recovers that one. Then you cannot hear any sound from the right side person. That is not good. That's why they combine, so that even though the replaced or retrieved signal is not a stereophonic sound, but you have a full recovery of the right side and left side. Got it? So our textbook explains that way. So the right side signal and left side signal is combined, and then we have a difference, so that in order to recover the right side signal, we subtract, we subtract, and in order to recover the left side signal, we add up these two, something like that. Got it? Okay. And also, in the figure, so we had some signal here, L plus R, and we had some pilot tone, and here we had L minus R, and also some reserved. So this is a baseband signal. So suppose you have, so this is not yet FM modulated signal. So that part was also misleading. So you have some real baseband signal, and that is the Fourier transform of left signal plus right signal. And then using the local oscillator and the frequency multiplier for this tone, so you have some carrier shift here. So you have here left minus right signal. Got it? Of course, here is a tone. So since the message signal, so this is modified message signal, because we have left plus right and left minus right. And this M tilde of T is a real baseband signal. You also have conjugate symmetry. So this is what you have. Got it? So in that part, I was a little bit misleading in explaining the material. Okay. So here goes the course overview. And we've spent a lot of time in covering chapter 3 and 4. And you may say that this is too slow, but it's okay. Got it? I have found is that other universities, they now have only 2 courses on communications. So first course covers all the analog and digital communications. So so around this one was the midterm exam coverage, and they are covering that part. And they have separate communication network course in the next semester, and where they talk about Wi-Fi and cellular standard. Compared to their curriculum, we have now 3 courses. One is this Introduction to Communication Systems. And in the next semester, we have Introduction to Digital Communication. And also we have Introduction to Communications and Networking. In that way, we may little bit slow down covering this important material. So from the beginning of the semester, I emphasized the importance of understanding the complex envelope of a real valued bandpass signal. This is the key to understand radio communication. That's what I told you. So this theme will appear again and again and again and again, not only as you've seen in the midterm exam, but also in the quiz 2 and final exam. Because I believe understanding complex envelope of a real bandpass signal is the key, is the core, is the essence of this course. And then you may easily build on build on the analog part and also the digital part. Got it? So I will talk about, since we have only 3 weeks around, I will briefly talk about this chapter 5, which is about digital communication. And actually, this will be hugely expanded in the next semester. In which course? In this course. And this course will be taught by Professor John Joseph, who has been teaching this course for a few years. So he will teach very well, and you will really appreciate the essence of digital communication. So I'm spending probably 1.5 weeks around. And then, as you see that these are all about random signals and noises, which I promise not to cover seriously. So I will skip that part and move directly to chapter 12. As I promised, I said that I will cover this last chapter on information theory and coding seriously. So that will be the topic. Okay, here goes the review of last class meeting. We, in order to analyze the effect of interference in angle modulation, especially in frequency modulation, we had what? We had this mark, right? A very simple model where message signal is 0, but still FM signal, desired FM signal is received. However, there is interfering signal with some frequency offset from our desired carrier. Then, what is the output? Which means the interfering sound at the output of our standard FM demodulator or FM detector, or if you discriminator. And we've seen that this tone becomes a huge tone signal in the receiver, possibly. So we had very simple idea of pre-emphasizing our message signal and de-emphasizing the output of FM demodulator. So that was one topic. And the other topic of our textbook was multiplexing. And we've seen this one already, especially about TDM and FDM. So in the frequency domain, we put different channel signals in this way so that the different channels do not interfere to each other. So this is the idea of FDM. And the difference from chapter 4's coverage, chapter 3's coverage on FDM was about this stereophonic FM. Right? So stereophonic FM is also does frequency division multiplexing at the input to the FM modulator. So you have L plus R in the baseband and L minus R in the kind of very small but passband. And we also have seen quadrature multiplexing, which is in digital communication called QAM. So some people just say this one as analog QAM. And the idea is like this. Since we are handling real valued bandpass signal, where real part of complex baseband times complex sinusoidal signal, if we take the real part of the complex envelope and the imaginary part of the complex envelope, then what happens? As you see that, we may put two baseband, real baseband signals. So real baseband and real baseband. If the channel is in the simplest case, it just gives us delay and scaling, then our received signal multiplied by cosine 2 pi FCT and low pass filter and our received real bandpass signal times psi, negative psi, 2 pi fct. This gives us the received signals. Actually, we need 2 here. So received signals, complex envelopes, real part, and imaginary part. So in this way, if this phase offsets are perfectly aligned at the output of the channel, then we may recover these 2 signals. And this is in the time domain. And what about in the frequency domain? Suppose we use DSB family to transmit these 2 real baseband signals with slight different carrier frequency. In that case, we may have to transmit in this way, right? So F1 and F2, or Fi and Fq, if we use DSB. However, by doing this quadrature multiplexing, actually, what we are doing is that we not only put this signal here, we also place the other signal in the same frequency band. In this way, we can save the bandwidth. So we transmit 2 signals, but we do not utilize twice the large bandwidth. And this must remind you that actually double sideband wastes the spectral efficiency. That's why people devised the idea of single sideband modulation. And also, as a trade-off between single sideband and double sideband, people devised the vestigial sideband. So this is possible. And this is quadrature multiplexing, or sometimes called analog quadrature amplitude modulation. Because in each in-phase component and quadrature component, you modulate this carrier only the amplitude part, and that carrier, the quadrature phase carriers amplitude part. So that's why people also call it analog QAM modulation. And there also goes PDM, and you know what it is. So you learned several different multiplexing methods. And whenever you have something similar, you have to spend some time to find out differences, dissimilarities. So sometimes the pros 장점 of one multiplexing scheme can be the cons, the 단점 for the other multiplexing schemes. So you have to well know about the differences of these schemes. For example, in TDM, the synchronization is a very important issue. So in the very old radio communications, people preferred FDM, even though it may less utilize the spectral efficiency. For the quadrature multiplexing, in the ideal case, you can save the bandwidth. However, in many crude receiver or transmitter, your local oscillators have phase noise. And phase noise may just make this in-phase and quadrature components interfere to each other. So in order to have QAM work very well, you need very stable oscillator, or if you cannot have that, you must be able to compensate for the phase noise in a tolerable level, into a tolerable level. So currently, this quadrature multiplexing, whose digital version, the QAM, is very, very popular in modern digital communication. For example, in your Wi-Fi standard, almost every signal you receive and send is a kind of QAM signal, even though you have to combine QAM symbols with so-called OFDM, orthogonal frequency division multiplexing. But anyway, so analog QAM's descendant is used in Wi-Fi. Also, our 4th generation LTE cellular standard and 5th generation NR standard also employs OFDM with QAM data symbols. So QAM is very, very important. So it's not just passed by person. You have to remember this terminology. At the end of last class meeting, I talked about possible amplitude distortion when we transmit an RF signal, especially even though we have constant envelope signal, something like this. So all the message information is contained in the phased angle deviation. If our channel, the realistic radio propagation channel, has multipath, which means that it's not a free space transmission, and also something's moving. Okay, there is some motion of, for example, transmitter or receiver or scatterer or diffractor and anything. Then what happens? This channel still, since radio wave propagates, this still system is linear, but it must be modeled as a linear time varying system. Okay, so in that case, in the extremely simple case, you may have time varying amplitude. So I've drawn this type of simplified case where you have so-called line of sight path and non-line of sight path, which is popularly abbreviated as LOS and NLOS path. And this one is moving away. Then what happens? So you have this path distance fixed, but that path distance increasing. Of course, the motion of such an object in our radio propagation channel may be slow relative to our data transmission rate, right? So it's not like our bus serving as a reflector in my radio reception does not move in the speed of light, right? It moves around 60 kilometers per hour or 30. However, if we use carrier frequency high enough, little bit of difference, time difference, has delay difference, may give us huge difference in phase change. So as you learned in high school physics and the introductory physics course, general physics or something in your freshman year, what happens? You may have constructive or destructive interference, superposition between these two signals. So here, amazingly, we may observe, even though this signal is a constant envelope, constant amplitude signal, you may have in the received signal, you may have to admit that this amplitude may now change. Okay? In that case, what happens? Without having bandpass limiter, our FM discriminator or FM demodulator based on differentiator followed by envelope detector may have a lot of distortion due to this time varying amplitude. That's why we had what? Bandpass limiter. Which is combination of limiter and bandpass filter before our ordinary FM detector. Got it? And about the wireless channel, especially this time varying channel, unfortunately, you will be exposed to it probably in graduate courses. Usually in undergraduate courses, we only talk about linear time invariant channels mostly. So even though you may take the EECE341, Introduction to Digital Communication, next semester, this topic may not be seriously covered. So this may be a good topic for your project. For example, you choose to collect some articles about linear time varying channel, wireless channel. And you may have good summarization, you may have good understanding, and make a good PowerPoint presentation file, and you record it after carefully understanding and memorizing all the scripts, and you send me. Probably you will be those among the 80% of students who get promoted in their final grade in the after the Christmas break. Okay, so that's the review part. Now let's have preview. So this chapter 5 of our textbook have 8 sections, and if we cover one by one, our time will be run up. So I'm going to talk very quickly about some important parts so that you have better understanding in the next semester when you take digital communications. And also, if you decide not to take the course, but you self-study the digital communication, I want this class meetings covering chapter 5 will help you to understand what is important and what should be remembered and what can be skipped. Okay, so here goes the PowerPoint slide of chapter 5. So first section is about digital baseband transmission. So take a look at the block diagram. So here goes big V. So suppose we are interested in still transmitting our voice signal, for example, cellular communication. What do we do? Still here you are, and here is a microphone. So your voice, the acoustic signal, acoustic wave, it passes through your microphone and becomes electrical signal, right? The microphone is very similar to a receive antenna for radio communication. And then this is what? This is an analog signal. And since our microphone has what? Converts this longitudinal wave, the acoustic sound, to what? To a change in voltage or current. So your signal M of T can be well modeled as a real baseband signal, and which is true. By the way, in the next semester, when I cover the digital signal processing, we are going to process around 2 or 3 types of these sources. Of course, acoustic signal. So after you learn some schemes, then you will process your signal or the acoustic signals after sampling, provided to you using MATLAB or Python, and you will feel the power of signal processing. Anyway, so here up to here, right? So the signal is analog in nature. And we've seen in previous chapters how our human beings have developed radio communications technology to transmit our voice or acoustic signal using radios, which means that electronic or electrical equipments that utilizes radio wave to convey the message, information. But we are not going to do that because, as you will understand after studying the effect of noise in communication systems, the noise is unavoidable in radio communications because in general, transmitter and receiver is located far away. Even though they are not located far away, interestingly, if the output of, the input to your transmit antenna is around 1 watt, then around just 20 meters, the output at your receive antenna will be around 40 dB. to 50 dB decreased signal. What does that mean? This means 10 to the negative 4, and this means 10 to the negative 5. So what does that mean? If you apply the power to your antenna, in Korean, 공중선 power, is around 1 watt. What you will receive is less than 1 milliwatt. It's 0.1 milliwatt, and this is 0.01 milliwatt, right? So signal, your received signal is very, very small. Why? Because if this is antenna, it radiates this 1 watt power to every direction, almost. Not every, this direction is very small, but almost every direction horizontally. And your received signal, probably looking similar, just picks up the power around here where your EM solver may translate this as some small size of aperture. And that aperture size is not that large, which means that, as you know, if you have a point source of wave, what happens? Its power density reduces inversely proportional to distance, and you have very small aperture. That's why this happens. So it's like your Wi-Fi transmitter is just around there. Your received signal power is around negative 10 dBm, which means that you have 0.1 milliwatt, something like that. Of course, your Wi-Fi transmitter does not transmit at 1 watt, but that's what I want to say. This is one, and the other is that in wireless communications, there may be interference in the same frequency band. So your interference, if you have not many information, may be well modeled as some random noise. Of course, we have better knowledge about the interference. We may design a better receiver to suppress the interference very well. So handling uncertain environment is necessary in radio communications. And when you handle uncertainty, there are many ways, but what you've learned in the curriculum of electrical and computer engineering is what? You use probability theory. And that theory has been very, very successful in better modeling uncertainties than other techniques like chaotic signal, blah, blah, blah. So that's why we have 전자수학 A, the probability and random processes course in our curriculum. And most of the prestigious universities' ECE department has that as a mandatory course. Anyway, so noise and interference is necessary because this signal is very small, so you have to amplify using so-called low noise amplifier. However, low noise amplifier, as the name says, has little noise, but huge amplification. But there is noise. That's the key. And this noise is all about actually the electrons in our circuit or metallic material pass through the grid of the material, but it collides the grid so that we have ohmic current flow phenomena. What is the ohmic material? As you've learned in your high school physics or freshman physics. Suppose you have two plates that have voltage difference. And suppose you have a charged particle. What happens? This charged particle receives what? Constant acceleration. So if we just have this situation and we supply charges, then your amount of current may increase quadratically, right? However, suppose this is not just a free space, but suppose this is a copper and you apply voltage difference. What happens? The free electrons in a metal is not free actually. It's different from just a free space with two plates with different voltage. It's different from that. The copper wire has what? Copper atoms. And you have electrons that is not bound to each atom. That is free electron. So this electron actually moves from one atom to other atom's orbit. The problem is that the atom is positive and the core, nucleus, and the electron is negative. So they interact. It's not a free electron, even though misleadingly it is named a free electron. Got it? So it accelerates, but decelerate. Accelerate, decelerate, accelerate, decelerate. That's why when you apply constant voltage, you have constant current in the direct current circuit. Otherwise, you must observe quadratically increasing current. Got it? Anyway, so as far as you have real world material that is conductive, then what happens? Usually that is ohmic material. 99% of them are ohmic material following Ohm's law. Actually, Ohm's law is what? Is an approximation. So if you carefully view, suppose we have omnipotent scope, oscilloscope, your current will be what? Every time electron passes, you will see direct delta function, right? As I once told you. And you have, even though you zoom out, but you will see a lot of variations, very high frequency variations in your current if you hugely amplify small signal. That's actually happens in the receiver's amplifier because your signal, received signal is so weak. Got it? Suppose this distance is 100 kilometers or 130 kilometers. That is around the distance between Pohang, the port, to Ulleung Island. Actually, my graduate student and me did some experiment, and the distance was around this one. And we just used 1 watt transmitter, and attenuation was around 110 or 120 dB. So suppose the transmitted signal is 1 watt, and channel gives us 120 dB attenuation. Then your received signal power is 10 to the negative 12 watt. And you now have a so-called low noise amplifier. And that amplifies the output of the receive antenna and drives the circuit. And we could extract the digital information. What does that mean? This low noise amplifier not only amplifies this small received signal so that it can drive the circuit, but also, even though the name says it has a little bit of noise, the noise is not ignorable. Because noise exists whenever we have an ohmic material in our circuit. Got it? And we cannot avoid using it, right? So that's what happens. In digital communication, we want to react to the noise. So we can overcome this apparently unavoidable effect of noise. That is the task of digital communication. So the idea is like this. So here, we have transmit and receive antennas because we mostly focus on radio communication. But be careful. After you learn mostly about radio communications, about antennas, about propagation channel, about some components, RF components, and modulation and demodulation schemes, actually, you can easily understand the other parts of communications, like acoustic wave communication or optical wave, light wave communication. They are very similar, but radio communication is one of the most complicated one That's why we focus on this one. And also this is very useful. Anyway, so here you have transmit receive antenna because we think about radio communication. And here is your source of information. And here is your destination of the information. And of course, this is called the channel. Got it? So between the transmit antenna and receive antenna, actually including antennas, we have radio propagation channel. And we don't know what will happen exactly. So what do? In communications, we design here encoder. And here we design, mathematically speaking, decoder. And this encoder decoder does what? Does something interesting. So in communications, the task is this one. We have information source and destination, and we have a channel. And we design two systems, this encoder part and that decoder part. Not arbitrarily, but cleverly after understanding the nature of the channel. So if the channel behaves differently in some other situation, usually we redesign our encoder and decoder pair. Got it? So in communications, it's different from signal processing. For example, if you just focus on this decoder part, and then you view this entire thing as a new source, right, of signal, your received signal or signal to be processed. In that case, you may say that decoder design or receiver design is the task of a signal processing. However, in communications, we not only design the receiver part, we also design the encoder part so that this pair better utilize the property of this wireless, of this channel, which may be a radio channel, which may be optical channel or other thing. So let me emphasize this one. In communications engineering, channel is the key. So you have to better understand the channel. And then you cleverly devise the encoding method and decoding method that best utilize this channel phenomena, channel's property, so that you can better transmit the information from the source to destination. Here, better means sometimes transmission rate, or sometimes error rate, or sometimes latency, sometimes reliability, sometimes some other, in terms of some other performance metric. However, what is important in communications is that according to the property, characteristic of channel, you design the transmitter and receiver part. Sometimes it is called encoder and decoder. Okay? So this is the big picture. And now let's compare my figure with the figure in the textbook. So here goes the channel, as you see, right? Here goes the source. Here goes the, not here. Let me draw. Here goes the destination. Got it? So you see? So got it? So you have source, you have channel, and you have destination. And we design what? We design this part, and we design that part. And this may be called encoder, and this may be called decoder. But sometimes it may be called transmitter and receiver or something like that. So in digital communications, when the source is, for example, analog source, what the encoder does is that first it digitizes the information, or it converts the analog information to digital information. And it may involve sampling, it may involve quantization, it may involve compression. That is the topic of information theory too. That's why This chapter 12, information theory, is better to be covered in this course than these things which are covered in digital communication. That's what I believe. So I'm going to combine kind of these two chapters, even though for a few class meetings, I will mostly talk about this topic and add some idea about information theory. So let's go back. So usually, I'm not saying that this is the only way. Usually, the encoder part has what? First, some source coding part. And source coding part, and this is related to source coding. So source encoding. So here, source encoding, and then channel encoding or channel encoder. And here, channel decoder and source decoder. Usually we have this structure, but not always. Be careful. Got it? Sometimes we cannot easily separate source encoding and channel encoding. But sometimes there is a theorem, mathematical theorem, where we can separate source encoding and channel encoding and source decoding and channel decoding without losing any optimality. Sometimes, especially we have single source and single destination, and we have some memoryless channel, blah, 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 blah. Got it? However, that situation where we have single source and single destination with possibly where memoryless modeled channel is so important, you may see a lot of transmitter that has source encoder and channel encoder separately, and you will see receiver that has channel decoder and source decoder separately. But that is not always true for multiple source and multiple destination cases, or when you have some strange channel. But anyway, so here, this ADC part can be viewed as a kind of source encoding. So you have converted analog message to digital some sequence, discrete time sequence. And then you do some line coding and pulse shaping, which will be covered soon. And then here, even though everything is omitted, you may have carrier generator, local oscillator, and you may have RF mixer, you may have some filter, you may have some power amplifier, you may have some antenna. Then it propagates through channel. Got it? And then your radio wave is received by receive antenna, filtered by pre-select filter, and amplified by low noise amplifier, and possibly image rejection filter and heterodyne receiver structure. And then you may have possibly two real baseband signals, in phase and quadrant. So even though it appears that there is only one sampler, you may have two samplers in reality. Some of you are taking lab for communication networks this semester, and your LabVIEW, the software that controls your software-defined radio, USRP, actually samples the in-phase, the real part and imaginary part of your received signal's complex envelope. So even though the figure shows one sampler, you may have two samplers perfectly synchronized in reality. And then you have D2A converter, and then you may have some message signal. Of course, there could be some digital signal processing part, and then you have your destination, something like that. So you will see similar structures again and again. But what is the most important thing is that source and destination and channel. And you put encoder or transmitter or decoder or receiver here. Got it? That is the idea of communication. And especially digital communications, we do what? Digital signal processing mostly. However, we can never avoid analog processing, especially which occurs around here and there at the input to the channel and at the output of the channel. Why? Because for example, in radio communications, we must have to handle electromagnetic wave, actually radio wave. And radio wave is no some sequence. It's a continuous time, some physical phenomena where electric field and magnetic field propagates through the space as a function of time and location. So we cannot completely avoid analog processing. You cannot remove antennas, right? Because antennas converts radio waves to electrical signal or vice versa. And as I told you, we want to increase the power applied to the transmit antenna. You cannot avoid using power amplifier in the transmit. And as I told you, you cannot avoid the use of low noise amplifier in the receiver because your received signal is so weak in radio communication, right? And one good thing is that when in the early stage of digital communications, most of the components were analog, as you've seen in some electronics hobby circuit. There is no digital component. Everything is analog, but you can still hear the AM or FM stations broadcasting very, very clearly. However, this digital revolution changed almost everything. So what happens? Except those antennas and amplifiers, and possibly some mixers, most of the parts are now being digital. So converted to digital circuitry. But you need some interface between digital and analog world. They are here, A to D converter and D to A converter. So what you do is that after you receive radio wave and you convert it using the antenna, the electrical signal, you just sample and quantize so that you have what? A sequence of bits. And then you use digital system. It may be some embedded system or it may be some dedicated digital filter. It depends on your design. You may use, for example, as I once told you, you may use LG Gram notebook to do everything. You put all the sensor input and output using the USB port to the notebook, and notebook has, for example, MATLAB working on that. It's possible. Or you may have specific ASIC, some special purpose chip that is sent to Samsung Foundry or TSMC Foundry, and whenever one design goes in, you have to pay $1 million, something like that. Okay. And they produce very, 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 very small chip. So for example, you go to the Lighthouse, National Lighthouse Museum in 호미, Cape, then 호미곶 등대박물관. You will see some very old equipment used in Lighthouse. Lighthouse not only has lights and Fresnel lens, but also they transmit radio wave so that the ships can better localize its position. That has been exercised from the early 20th century, actually. Immediately after the invention of radio communication, they started to use radios for radar and something. And in the museum, they display very old equipments. And for me and for you to see inside, they replaced the metallic cover to an acrylic transparent cover. And you will see this huge size of capacitor and inductors. So old lighthouse and ships had very huge equipment in order to receive and transmit some radio signal. Now, probably this size of equipment may perform much more complicated operations, mathematical operations. It's all thanks to the fast growing industry of electronics and semiconductor engineering. So throughout this course, I emphasize that there are two buildings, and they rarely actually communicate. That's the problem. However, in one side of the building, people think about mathematical, logical operations. If it is done by some electronic equipment, we may be benefited. And in this building, there are guys who turn inanimate materials to intelligent systems, right? Some silicon, metal, and combination of chemicals, suddenly it does what? GPT-4, something like that, right? Similarly, we may have very small chip that does a lot of complicated operations that asked by those guys in the right side building. And they revolve, influencing each other, and that is the result of this wonderful world of electrical engineering system era. Anyway, so ADC and DAC are essential in digital communications and digital signal processing and all modern digital electronics. Because we can never completely avoid digitizing some analog signal, because acoustic wave is in nature analog. Our light wave or radio wave are in nature analog. However, in order to make everything very simple and our system performs a lot of complicated mathematical logical operations and follow procedures, we need to convert these signals back and forth the digital format. So some of you, not all, may major in ADC forever. Some of you may major in DAC forever, because these are so important. And you may say, that, oh, what's the big deal? Just to sample and quantize. The problem is that, as I told you, here you may have to have almost perfectly synchronized two A to D converters operating very, very fast. For example, suppose in your receiver, you want to directly sample the RF signal after you just amplify using low noise amplifier. And its carrier frequency, suppose it's 3 gigahertz, even though signal bandwidth is 100 megahertz. Now, according to your sampling theorem you learned in signal gen systems, you may at least require 6-point-some gigahertz sampling rate. What does that mean by gigahertz sampling rate? You have to sample 10 to the 9 times within a second. And you must have parallel two ADCs perfectly synchronized. Otherwise, you may have a lot of phase difference. As I told you in that two-pass model, slight timing difference may give us totally rotated phase. So for full digital RF system, you need very accurate, perfectly synchronized DAC and ADCs. And actually, that's the task right now. We want to convert as many parts of our radio equipment as digital parts. And we need very fast, perfectly synchronized, very small error ADCs and DACs. Anyway, I'm so nervous today. Anyway, and here goes the topic named line codes. And we are almost out of the time. We have 2 minutes. So what is a line code? Line code is a very simple encoding method of the output of ADC. So suppose you have ADC. What does that mean? You have analog input, and here you have digital output. What does that mean by digital output? ADC usually has samplers, right? Uniform samplers, usually. I'm not saying always. So at each sample, you assign several bits. Suppose you have 16-bit revolution, some 3 giga sample per sec ADC. Now, how many bits you obtain at this output per second? 3 gig times 16 bits. So 3 times 16 times 10 to the 9 bits per second, right? A lot, right? Now, line codes does this one. Suppose you have first 16-bit, and then you have MSB to LSB, most significant bit to least significant bit, right? So you form a sequence, a mathematical sequence from some initial in time index n, okay? So what you do is that, for example, you assign this one as A1, and A16. And then your ADC generates in the next sampling epoch 16 bits. And then you have A17 to A32, right? In this way, you may construct a sequence of bits. And to make everything simple, let's say each bit is either 0 or 1. And then you have a sequence of zeros and ones. And line codes is very simple. You convert this sequence of bits to a waveform. Okay, so encoder for line codes converts this sequence into a continuous time signal. And different line codes, encoders for line codes, generate different waveforms. So this axis is time t, got it? This is time axis. And if you have a non-return to 0 line code, this 0, 0, 1, 0, blah, blah, blah sequence is converted to this analog signal. Energy mark converts differently. Unipolar return to 0 converts differently. Polar return to 0 converts it differently. And bipolar return to 0. And here goes Manchester code. And there are many other line codes that encodes this sequence of 0 bits to a very simple waveform. And each one has different time domain characteristic and also frequency domain characteristic. In time domain, you find the differences and commonalities. And especially when you find the commonalities and differences, because there are too many NRG and RG, see what happens in each interval for each bit. Non-return to 0 means that, as the name says, the value is not necessarily returns to 0. But here, for return to 0, you will see, let's see this interval, okay? See that? You have a value 0. So your value of the line encoder, this unipolar RG encoder output goes to 0 at each end of the intervals. Got it? So in this way, they devised different line coding schemes, and different line coding schemes find different applications. And that will be covered in the next class meeting. Okay, that's all for today.